Yes. So space, people have been trying to race into space in the past. So this is, of course, one of the mementos from the human space race. And I think it's fair to say that while the Americans might have got to the moon first, the Soviet Union had the best propaganda posters. They're still getting reprinted and used in presentations because they're so dramatic. And the Americans, not quite up to that in terms of propaganda. The problem with the whole human space race was, of course, that it was mostly propaganda. It was a brilliant, amazing technical achievement, but it was mostly done essentially showing who got the bigger economy. Once that was done, interest kind of waned. And that's why we still haven't had anybody walking on the moon since I was a kid. And that is kind of sad, because, of course, space is big, really big. That's where everything except Earth is. Which might mean that there is actually quite a lot of valuable things. Now, people have, of course, also been thinking about that there could be aliens out there, and they might be traveling around and trying to make use of it, like coming here and stealing our women. Because obviously the terrestrial women are as appealing to them as we find them appealing to us. I mean, who wouldn't want one of these big-brained beauties at home? Of course, as more changed and as we shifted away from maybe 1950s pulp fiction, people started thinking about other reasons why aliens might show up on our doorstep and be nasty. And one possibility might be, of course, that we're stealing our water and other precious natural resources. This is very much a worry that kind of shows up mostly in science fiction in the 70s when we started getting environmentally conscious. But it actually exists already in H.G. Wells' War of the Worlds. He was basing this partially on the idea that Mars was an old planet that was declining. And the reason the Martians were coming with the war machines to conquer England was basically that it was much nicer than Mars, even though it had this horribly heavy gravity and lack of red vegetation. But that's not anything a few death rays can't solve. Unfortunately, they also, of course, discovered that there was the flu, and the rest is history. So this kind of story of alien civilizations coming to our doorstep to steal our water still feels a bit weird. But a lot of the question is, of course, why aren't we seeing any aliens, whether they want water, women, or just to tell us that they have a holy book that we really ought to read? So this is sometimes called the Fermi Paradox. So in the 1950s, Enrico Fermi and many of the other leading geniuses at the Manhattan Project, during a lunch break when we're not working on the hydrogen bomb, got into a conversation that began with a cartoon in the New Yorker about where are all the waste baskets in Central Park. And maybe it's little green men in flying saucers that are stealing them. And the physicists started talking about, well, what about space travel? Can we do it? And they were pretty confident that that should be doable, especially with nuclear rockets. Then they started thinking about how big the galaxy is. And then they started to realize, yeah, and it's fairly old. By that point, we were still very uncertain about the age of the universe. Indeed, many cosmological theories back there suggested that the universe was infinitely old. And that led to the realization, wait a minute, this place, there is a lot of places where intelligence could emerge, and it's been around for a very long time, and it should be possible for it to travel around. Why aren't we seeing anybody? And that is, of course, Fermi's question. He just said, where are they? And the answer to that question might matter quite a lot. As was mentioned earlier, I'm at the Future of Humanity Institute. Why do we care about aliens? And the reason might be that the silent sky tells us something very important about our own survival. So even if we actually didn't care the least about the aliens, we might still say there is good evidence there. So if astronomers had instead constantly been observing alien ruins or civilizations far away doing various things, we could probably have developed the science of xenology, doing statistics saying that 9 out of 10 super civilizations we see in the far universe do these things. Or it looks like all the planets with ruins on them have the following characteristics. We better not behave like that. Right now, however, we're just seeing an empty sky, which means that there might be quite a lot of possible explanations. And no, I'm not expecting any of you to actually be able to read this, even if this had been well in focus. And this is just the ones I could fit in on one slide. There is a very nice book by Webb called 75 Answers to the Fermi Paradox. It's the second edition. The first edition was 50 Answers to the Fermi Paradox. I have come up with one extra, but he couldn't fit it into his book. So I'm waiting for the third edition, which is no doubt going to be 100 answers to the Fermi Paradox. The first set of answers is very simple. Oh, there are no aliens. And maybe that is just because intelligence is very short-lived. You become intelligent, and then you invent something that destroys you. And this is the main reason we at my institute are really interested in this, because if that is true, we're in deep trouble. Also, it's a very tricky trouble to get out of, because presumably a lot of other civilizations would also have noticed this fact and tried to get out of the hole. It might also be that intelligence is really, really rare. It might be that life is super rare. You need a ridiculously unlikely combination of molecules to get the first biomolecules, and that only happens on one planet in a Google. So we are essentially on the only planet with life. That would make this planet really precious. Or it might be that life is really common. Just get a puddle of organic goo on the planet, and 10 minutes later you get the first very simple precursors to life, and then it takes over. Except that it never evolves to anything interesting. If you think about the history of Earth, life has been around for a fairly long time here. And several of those billion years, we don't know much has happened. There is actually a term, the boring billion, which is basically after Earth got a bit of oxygen in the atmosphere before the Cambrian explosion, where we started getting a bit more complicated multicellular life, where very little happened except that occasionally the planet almost froze over a number of times. But that was a billion years where we don't really see much happening. There was probably a lot of evolution. The cells were probably learning how to do a lot of biochemistry. But you could imagine a slightly lazier form of life that had the boring trillion. It takes 1 trillion years before it comes out with, hey, if we glue some cells together, we can make something that crawls around and gets more nutrients. Now, if it takes 1 trillion years to come up with that, unfortunately, the sun burns out before you're done, and that's it. And maybe it is that life actually tends to evolve more easily towards this kind of slow life than our inner life. But we don't know. That would be very good to know. Another possibility might, of course, be that we conceive aliens, just like you conceive a PowerPoint. So one thing might be our own limitations. Maybe they're so incomprehensible that we don't even understand what we're seeing. Or we might not have been searching properly. The budget for searching for alien intelligence is not that big. Mostly people laugh at you if you propose that as useful telescope time. So we haven't been scanning the stars that carefully. There might also be a problem that it's hard to actually transmit radio messages far away. So it might be that we missed it. Many of these explanations sound reasonable from the start, but every year we're keeping on observing, they get less and less likely. Another possibility might be, of course, that the aliens are doing other things. Maybe they're all kind of Stone Age, or maybe they're all meditating monks living in harmony with the environment and not building any rockets, so we can never observe them. Or they invent something like World of Warcraft and spend the rest of their lives playing virtual reality games forever. Or they develop a technological singularity, turn into superintelligences, and disappear in a flash of light somewhere. Or they migrate away from galaxies, because galaxies are full of supernovas and dangerous aliens and other things, so they're not. Many of these explanations sound really good, and you can make great science fiction stories out of them. But they all require all individual aliens and from all species to do the same thing. That's kind of weird, because if I were a sociologist and explained, my theory predicts that all humans in all cultures across history will do this thing, I would be laughed out of the room. I would be obviously a mad scientist. The sociological explanations are never that strong, even for humans. And why should we then believe this would apply maybe to intelligent crystals from another planet? And then, of course, you have a conspiracy theory thing. Oh, they're actually here. They're secret in cahoots with the powers that be and the Illuminati, and they're probably advising Donald Trump or something like that. That might be what his toupee is. And the evidence for that is actually not very good either. It's rather hard to maintain a good conspiracy these days. So these explanations, they're all kind of unsatisfactory. If one of them is true, it's going to turn out to be a really weird one. So now we're going to turn back to us, the question of how do we go about maybe trying to settle space. So far, this is about as well we have done. We have gotten up to the space station. We have made a few tracks on the moon. Indeed, if my train from Oxford earlier today had gone straight up, I would have been in space. Except, of course, that space is not so much a location as a velocity. If I were just placed 100 kilometers up, I would slowly fall down and I wouldn't get anywhere. I would need a lot of velocity to start orbiting Earth. The trick to get to space is, of course, to get an awful lot of velocity. Now, how do we do that? Well, we have rockets, which unfortunately are run by my least favorite equation in all of physics, the rocket equation. Learn to hate it. What's actually going on in a normal rocket? Well, you have a rocket, you set fire to it, it starts expelling stuff in the back very fast, it moves forward. If you think about it, the center of mass, if you have a rocket in space right in front of you, is right in the middle of the rocket. It starts moving away. The center of mass actually stays in the same place. The rocket goes off here, slightly empty because a lot of gunpowder or propellant has been expelled, and the propellant is going off here. The average location of the mass is still exactly where it started. So if you had just as much propellant as the rest of the rocket, they would move apart in exactly the same speed. That's kind of neat, but I want to get there fast. How do I do that? Well, one solution is to expel it very, very fast. Now I will get a bigger speed here. Another thing is, of course, if I could take a much bigger mass and move it back here. That would also speed things up. If it was just a tiny part of a rocket that got propelled and the enormous mass moving over there at a modest speed, I would also get a pretty good speed. And this is, of course, what we're doing with actual rockets too. It's exactly the same thing as fireworks. The problem is the speed of that exhaust is dependent on how I build my engine. And unfortunately, most of the engines are basically like the fireworks. You set fire to a mixture of something. Of course, it's slightly more exotic things in one of the SpaceX rockets, but not that much. You still have basically an oxidation reaction going. And the problem is that has basically a maximum exhaust speed. You can't actually get enough energy to get an enormous speed of exhaust, which means that you need to do something else, like having an awful lot of reaction mass you spew out, which is why most of that rocket is not really payload. Those satellites that go into space are a tiny, tiny pinprick at the top of that nose cone. And of course, in the past, we were also just dumping the entire rocket after use. At least modern reusable rockets are reusing some of it. But it's a terrible waste. And this is all the rocket equations' fault. I'm only going to show these equations in the entire talk, I promise, but I just want to teach you to hate them. And this tells you that the change in velocity I get is going to be equal to the exhaust velocity times the logarithm of ratio between the total mass divided by the payload. Or you can rearrange this and get that if I want the amount of mass I need to put in the rocket goes up exponentially with the speed I want to get. That's very bad news because I want things to go really fast. If I want to actually leave Earth, I need to move 11 kilometers per second. That's a big number, which means that if I can't get an enormously large exhaust velocity, I would need to end up with an enormously large rocket, which is going to be expensive, bad for the environment, and a real headache. So yeah, generally, this is the reason to hate the rocket equation. The problem is, of course, it's kind of a law. It's based on physics. Deep down, it's just because of my initial rocket example. When I'm started to move a rocket, I have all the fuel that I haven't burned yet, but I also need to accelerate so it moves forward. And that, of course, means that I need to push, have a bit of extra fuel to handle that, and that extra fuel adds a little bit more. That's why you get this exponential term. extremely sad. Now, can we do better? It seems like we probably could. We can probably do fairly well with chemical rockets. Elon Musk is certainly doing pretty fine. And his competitor Jeff Bezos is also doing relatively fine. Personally, I think we should be going for nuclear rockets. Now, there was an awesome project in the 1950s led by Freeman Dyson and some of the other people who hang around Los Alamos and other similar places about using nuclear explosions to propel rockets. Basically, you have a little nuclear explosion, it pushes against a very thick dampening plate, which pushes the rocket. You put out another little nuclear explosive and but very much louder. This project, Project Orion, is probably one of the most awesome projects never built, and we should probably be fairly thankful it never got built. Again, the environmental impact statement would have been dire. The principle is still interesting because the chemical reactions don't produce enough energy to give you a good exhaust velocity. So another method is to actually have fuel run through basically a nuclear reactor that heats it up to high temperature. And now you can get a pretty impressive rocket. You can also decide to go a bit more fine and high-tech. Instead of trying to use big engines, you just take xenon gas, and you ionize it, and you accelerate it so it's going off in a very high velocity. This is an ion thruster. And on one level, very, very wimpy. You're basically sending a beam of very thin gas back. So the acceleration is really weak. You can't lift from Earth using this. But on the other hand, you can just keep on doing this as long as you have a gas tank and you get a very good velocity. So over time, that can build up quite a bit. So you can put on some solar panels and actually do some pretty awesome things. There are some other interesting ideas about using electrical methods too, which are still more on the sketch pad. And then you can, of course, think about not using rockets. Solar sails has both a romantic air to them, and it's actually a sensible thing. Basically, sunlight, it exerts a weak force on things. So if you have sufficiently thin aluminum foil, and you can direct it and actually use that. And since the sun is up all the time in space, you can actually use this to maneuver around in the solar system. The main problem with solar sails is that it's very tricky to handle that kind of thin aluminum foil. Normal household aluminum foil is a bit too heavy to be a good solar sail. And actually building a solar sail that is really thin enough and light enough, but wide enough to work, is a really tricky origami problem. You need to fold it up first so you can launch it into space and then unfold it. And many of the experiments have so far failed because it's so hard to unfold this relatively sticky thin film. People are working on it though, and it's looking rather promising. Okay, generally, of course, we have actually demonstrated that we can get to space and even fairly remote systems. We have also demonstrated that we can actually construct habitat where humans can survive for years. We haven't demonstrated it in space yet, but actually making closed ecosystems seems to work if you're willing to eat relatively bland food. But basically ground-based closed systems, without the flair of Biosphere 2, where we try to have a jungle and a swamp and a coral reef and a lot of fancy and interesting stuff, but instead of just having essentially vegetables growing and providing oxygen, that actually seems to work. Of course, the visions people have been having are slightly more grand. So in the 1970s, Gerald ONeill at NASA was envisioning, what should we do? And he was arguing that the surface of a planet is the wrong place to have an industrial civilization. We should essentially putting our industry in space where you get sunlight all the time. You could build giant solar panels that send down the energy using microwave beams. Convincing people that those microwave beams are safe is another matter, but he was optimistic about that. And then, of course, you can build these rotating cylindrical space stations that later have become known as O'Neill spheres and O'Neill cylinders. And Jeff Bonsall and many other artists made these very appealing pictures showing your future in space, which quite often looked very much like an idealized California. Some of them also look a little bit like the cover of the Jehovah's Witnesses journal, kind of your salvation up there in space. The problem was, of course, O'Neill said, yeah, this is relatively cheap. It's just the cost of another Vietnam War. And at that point, people said, nah, we can't afford that. So people kind of stopped investing in this. It's worth noting that Jeff Bezos, of course, is a fan of O'Neill and kind of want to revive much of this. The real tricky part here is coming up with a great business plan for space. Communication satellite, yes. Spy satellites, yes. Space industry, there is like that standard internet joke, something, question mark, profit. We still don't know how to do that. But it seems like at least technically one could probably build this if you actually had enough space industry up there. And before we get to that point, of course, we might consider, could you actually prove that space settlement is possible? So I'm writing this big book about grand futures, and I'm working out in excruciating detail the minimum viable vision instead of setting space. Not as something we should be doing over the next few decades, but just proving that you could do it. So instead of going for these beautiful cylinders and toruses, imagine something like the International Space Station, which is a pretty crummy place to live in. But some people are enthusiastic enough to spend months and years up there. So basically, it turns out that it looks like we can go through a checklist that we can escape the gravity. Even with our own crummy rockets, we can do that. We can transport things around the solar system. It takes a long while. We have life support that works well enough. The recycling has not been demonstrated completely yet, but I think nobody really disbelieves that we can do enough recycling. Radiation protection in low Earth orbit, yeah, it works. People are not super healthy after being in space. And I think if we were serious about going deeper, we could actually put, for example, the water tanks around the habitat so people would survive. We don't really know whether there are other gravity-related things that would do people in the long run. And reproduction is an interesting question. Do we need gravity to actually have proper reproduction? One part is, of course, the mechanics of sex, which a lot of people have been thinking too much about zero-gravity sex, and it probably is absolutely horrendous. But pregnancy might also be affected by gravity. There are some arguments that actually you might need artificial gravity. Now, rotating space stations actually is a fairly simple thing. The reason the International Space Station doesn't do this is that they want to do experiments in microgravity without having any gravity. And adding moving parts was kind of too tricky. But for example, having a space station connected with some cables to a counterweight and rotating the whole shebang, that seems to be eminently doable. And it's just a shame that we haven't tried that yet. Getting energy in space is easy. So solar panels work really well. The thing that we need to demonstrate, I think over the next few decades we're going to get actual demonstration, is gathering materials, whether from asteroids or the moon, and manufacturing stuff from it. And in some cases that could be easy, but you really want to demonstrate parts closure, that you can build all the parts of a space station in space. There are also some risks that we haven't quite demonstrated that we can handle, and that we can do it open air. But were we to be able to check all of these, we would actually have a proof of concept that you could really live in space. That would correspond to living in something cramped without nature like the International Space Station. Most of us would go mad within a week. But we select the people who don't go mad within a week, but think this is great. And then they have children, and they manufacture more stuff out of asteroid material and build another space station, and the kids move over there. Now, if the rate of building new space stations is slightly bigger than the rate of other space stations crashing, in that case, you can prove that we can totally settle the solar system. It's interesting because this is something one can actually work out in fairly high detail what's necessary and actually make long parts lists and try to investigate what we should do research programs to really prove. And I think most people would be convinced that, yeah, this could be done if we really cared to do it. Now, if that happens, then we have basically all of the solar system to our disposal. And we might hope, of course, that we could do it a bit better, that we could actually get this rather than being crammed up in the ISS. But it seems like the total amount of stuff we can get in the solar system is pretty astonishing. So if we think just about the asteroid belt and asteroids, we basically have 10 to the 21 kilogram of matter there. And we could get into this very weird ecological niche. As humans, we make new ecological niches all the time. We invented the ecological niche agriculture, which is great if you happen to be corn or maize or rice. and maybe not so great if you happen to be other species, but very good for us. Or we invented the ecological niche of human cities, which is great for humans, pigeons and rats and some other species. And we could invent the ecological niche of taking asteroid material, process it using solar power to build habitats that process more material and build more habitats. And basically, the top kilometers of Earth's crust is about 10 to the 12 kilograms of matter. That's the matter we normally build our cities and our biosphere and our coral reefs out of. We get 10 to the 21 kilograms in the asteroid belt. And again, the wonder of exponential growth is even if we have a crummy scenario with these International Space Station copies, they're slowly growing. Even if they make a copy every 20 years or so, eventually the exponential growth wins and all the asteroid belt is space stations. That's room for at least 1 trillion people. Exactly how many people you can get in depends very much on how much living space you want. That's kind of a choice up to us. The main limitation here is probably the amount of nitrogen you can get hold of, because asteroids are pretty dry. There is enough ice, but I don't think we will get enough nitrogen to run a thick biosphere. This is where we might want to actually send some people off to Titan and start getting its atmosphere. Now, if there was inhabitant of Titan, now they might actually say we're getting invaded from space by these horrible aliens from a very hot planet. But I think it's pretty unlikely that there's life on Titan. It might very well be in a life hiding under the ice of Enceladus and Europa and other places. So there might be some interesting surprises out there. But it doesn't look like there are many intelligent species in the solar system. We might be one of them, hopefully, but we'll see. Okay, so now I've been arguing that this is the least we can do, because I think we can do much better. The limits of physics are interesting. If you imagine a diagram of what we can do technologically, there are some outer limits set by physics. Certain machines can't be built because we collapse into black holes because we're too heavy. Some machines can't be built because of light speed limitations and boring things like that. And then the other machines, well, that is the blue corner, that we actually do have. And then there is this interesting area in between where you can do exploratory engineering, where you can work out if we had the ability to build this, it would work, because we base it on stuff we understand well. So one thing is, of course, that we already do it. So we know we can do a lot of solar panels in space because we already put a lot of solar panels in space. Also, generally, if nature can do it, we typically can do it. Sometimes it's harder than we expect, but we have made, for example, self-replicating machines. They're called computer viruses. They're not terribly nice ones, but it's a proof of concept. I think that we're going to get better AI. For my argument, I don't need super intelligence or even human level intelligence, just animal level intelligence. And one of the cool things is we can automate our tasks. So if I can automate something I do, good, I can leave it to the machine. I can also make the machine run faster and make more copies of the machine. Typically, the output is not going to be equal to what I can do, but an order of magnitude or more better. If I'm making paper clips, that's going to be a few paper clips per hour. If I have a machine taking wire and turn it into paper clips, that's going to be thousands or hundreds of thousands of paper clips per hour. And one of the interesting things is, of course, that building infrastructure can also be automated in the long run. And one of the things here is, of course, that means that we're not going to be scale limited. Basically, if you have, let's say, a mining robot that digs up asteroid gravel, puts it into a hopper, and another system kind of melts it down, separates the elements, and turn it into robots, hoppers, solar panels. Now I can have a system that I put on an asteroid. It starts taking asteroid turning it into more robots, more factories, and before I know it, I have infrastructure and no asteroid. That means that basically the limits are going to be kind of energy, the ability to control, which we might want our software to do well. Otherwise, we need an awful lot of people sitting and keeping an eye on things, things like time and entropy and knowledge. Now, you can use this to transform the world a lot. Basically, you can pick apart planets. I worked this out in a paper with Stuart Carlson. You get energy, you mine stuff, you get it into orbit using launches, you get more solar collectors, you repeat. It turns out that under certain assumptions, which we might quibble about, it takes us about 40 years to pick apart Mercury. Now, why would we want to pick apart Mercury, you might ask? And the reason is that I want to use that to build a Dyson Sphere. Dyson Spheres are awesome. Freeman Dyson came up with this idea, although he very much admits that it was Olaf Stapledon who actually had the original idea. He just wrote a paper in a scientific journal about it. So he observed that, well, our energy use is going up exponentially. Eventually, we're going to use as much energy as the sun outputs. Can we actually harness that? And he argued that, yeah, actually, it's not that weird. You just put solar collectors into orbits around the sun. And he was suggesting this in the context of looking for alien intelligence, because if you see a star that is mostly emitting its energy in infrared, and occasionally get glimpses of a normal star between a lot of solar collectors, then you should probably suspect that something weird is going on. And people have been looking for this ever since with no success. But even if no Dyson Spheres exist out there, we can build them. And they have some wonderful properties. If you put up solar collectors around the sun, you can get 10 to the 26 watts of power. That is a lot. That's way more than we are using right now. And of course, if you actually use this to build habitats, you would get several square astronomical units of living area. The population use that could live on this one would be totally ridiculous. If you instead use this as a server farm, so imagine that you have solar panels on the back of them in the nice cool cold of space, you put microprocessors, then the limit seems to be something on the order of 10 to the 49 operations per second in total. The lags between them is that's kind of problem, because this is a light minutes across. So you might want to have some very clever algorithm allocating your computations. Otherwise, the delays are going to be really annoying for the users. The users might, of course, be actually software running of a system, and in that case, maybe they don't notice the delays because they are also delayed. If you put sensors on the outer side, now you have actually a potentially very powerful telescope. You can literally read the alien newspapers a galaxy over. And you can use this to, of course, send off radio wave or laser to communicate over very long distances, especially if the receiver also got a Dyson Sphere. And of course, if you amp up the power, now you got a rather nice laser to blow up planets with. The interesting thing about this is that it's actually fairly useless as a weapon. It's terribly impressive in one sense. And it's very much of a threat if you know where somebody is. But if some people are sitting on a spacecraft moving around a bit randomly, they're light years away. You have no idea where to aim your gargantuan laser. And it actually turns out that it's very hard to hit somebody in a solar system, even a light year away, even with all of this. So actually, I think this is mostly a tool for peace, fortunately. You can also actually use this to move entire stars. I don't have the time to get into this, but I actually worked out how to literally move an entire galaxy using Dyson Spheres. But it's a slow process. But you can, of course, use this energy also to accelerate spacecraft. After all, you want something moving fast. You want to impart a lot of energy to it. Because getting back to the interstellar craft, it's actually worth noticing that we could send a craft to the stars in 1970. The Voyager probes, if we had aimed them slightly differently, would have ended up in some other solar systems. They will, of course, not be workable at that point because there's going to be inert lumps of metal, but they do still contain a golden recording and a little bit of art, etc. We can actually launch things over interstellar distances using chemical rockets. It's just that it takes tens of thousands of years, and we don't have technology that holds together well enough over those time span to do anything interesting. And also, we kind of get annoyed by waiting. Then there are interesting projects like this one, Project Daedalus from the British Interplanetary Society. They're awesome. They have done some of the best exploratory engineering ever. In the 1939, we did a survey on, could you actually send a man to the moon and bring him safely back again? And based on the best technology and understanding they had a sketch for doing that. That might have been workable using a solid fueled rocket. And then the war happened, and they essentially said, okay, we have other things to work on right now. The first thing they did after the war ended was, in the light of the V2 rocket and what we learned from the Blitz, they updated the paper with liquid fuel, and now it was much easier to get to the moon. This is a project they did in the late 70s about a fusion-powered rocket, a little bit like Project Orion, but You have small pellets of deuterium and helium. You use laser beams to compress them. They detonate, and that move you forward. So they have these fuel tanks containing a lot of deuterium and helium, and you get to move to Barnard Star. And I don't remember exactly the mission length, but it was probably on the order of decades. Now, 40 years, yes, yeah. Which I think that's totally doable. And it's very much in the range of, you can imagine, a lifetime project. You start as a PhD student and you get to see some of the results. Now, it's awesome. I have a book. I really love it. One can quibble endlessly about details. The chapter on the software is quite fun to read today. But it still suffers from one thing, and that's the darn rocket equation. The rocket equation is, of course, going to mean that you need an enormous amount of fuel to accelerate the ship, and then the rocket equation to slow down at the destination. So this is pretty big. So what else can we do? Well, another thing is, of course, what about external launchers? You have a laser beam, you have a solar cell. So this is what the breakthrough Starshot people are working on. So they're hoping to do this very small spacecraft. Instead of sending one, they have an enormous flotilla of them. They use a giant laser battery down in the Chilean desert, accelerate them towards Proxima Centauri or Barnard Star. I think it's mostly Proxima these days, but and at 20% of light speed. And again, they want a deadline here in the order of decades, so they can actually get the data back before the benefactor of the project gets too old. And I think this looks promising. There are good engineers involved, and a lot of physics seems to work out. There is an awful lot of practical stuff to do. And the lovely thing that makes me love this is, of course, no rocket equation. Because you're not carrying any fuel in that system. All the fuel is in some sense on Earth. The downside is that it's slightly hard to break. I think there are tricky ways you can actually do that. Another problem is, of course, Einstein has kind of trapped us. We have a light speed limit too. And let's just say that the rocket equation gets even worse when you add relativity theory to it. It's really nasty. But that is still, well, that's much faster than most of the rockets we consider. But 20% of light speed, Einstein starts to bite a little bit, but not enough that you actually get a problem. The real problem you get there is dust and small particles. So basically, as you approach the speed of light, the hydrogen in space is becoming more like a proton beam, which is kind of nasty. And of course, already at 3 kilometers per second, if you collide with a piece of gravel, that explodes with the corresponding for the amount, like it had been made out of TNT. That's at 3 kilometers per second. That's even kind of slower than escape velocity. The problem is, of course, that once you get about 86% of C, then it's like it actually turns into energy, which is really nasty. So you might want some kind of shielding. This is a Whipple shield, which is one approach NASA has been using. So you have several layers. The first one kind of hits and something explodes, and then that explosion gets stopped by some sequence shields. So you want the various things and to protect your craft when it goes really fast. And the annoying thing, astronomers haven't told us how much gravel there is in deep space. We don't know. We know that there is a lot of dust. If you stand on a very nice starry night and look on the Milky Way in a place without any light pollution, you will see these grand streaks of dust along the galactic plane. That's because every photon coming from beyond that gets trapped by a piece of dust. However, that's usually very fine dust. The total, basically, when you do a calculation, you realize that the finer the dust is, the better it is up to a point at capturing the light. So the gravel that we are worried about, that doesn't show up. And indeed, astronomers have a hard time observing it, so they don't tell us very much about how much there is. If you try to extrapolate from what they say in their papers and books, they generally say there is not much beyond a few microns in size, which would be super reassuring. There's some radar observations that hint that maybe there is more. We don't know. The Starshot people might be the ones to just figure it out by just sending something very fast and see what hits it. But I'm not super worried, but I think it might be actually one of the big limitations. It also suggests, of course, that yes, you need shielding, and you probably want a spacecraft that's more like a Javelin than a standard rocket. This, of course, means that that kind of square-jawed space hero Actually, he doesn't fit in there. Besides that proton radiation and that even at 20% of light speed, that means a few decades in space, this is not really going to be that suited for people. This looks like a job for robots, ideally very small nano-robots. Now, you can do the math, and I'm not going to bore you too much about the allowed region, but it seems like for small probes, running into dust is a big problem. Also, it's very hard for a really small probe to actually have a good retro-rocket. Basically, you can't scale down a chemical rocket or a nuclear rocket or an antimatter rocket beyond a certain size, simply because you need enough matter to hold in the exhaust. So you need to go above a sort of thing. There are also limits on how much energy you have in accelerating. If you have a Dyson Sphere, you can actually push that limit rather far. In the end, you end up with weird things like heating because of the medium you're passing through. But most likely, the main limitation is actually going to be dust. So that might put a distance limitation on how far you can travel. You probably can't see this very much at all, but basically, if you can travel, let's say 1 light year, you can't actually get anywhere because the closest star is more than 1 light year. If we can travel, let's say, a little bit more than 4 light years, we can get to Proxima and Alpha Centauri, and I think 1 other star. But that's it. If we can travel a little bit further, we might get a few other stars. If we can travel about 8 light years, suddenly we can get to a bunch of stars that allow you to get to other stars and basically get a full network. So if you plot the fraction of stars that you can get to as a function of how far you can travel, there is a sudden transition where you go from practically none to all of them. And basically, if we can just travel a little bit more than 8 light years, then we can take most of the galaxy. That's a lot of stars. That's about 300 billion stars. And each of them most likely have solar systems with asteroid belts and planets and all that lovely stuff. And even if we travel really slow, like sending off colony ships at 1% of light speed, and spend 5,000 years on each new solar system building up stuff and eventually saying it's crowded and polluted around here, let's go somewhere else, then it just takes a few million years before we have settled the Milky Way. This is another way of seeing why the Fermi Paradox really bites. And of course, this is a lot of resources that you can use. So this is another reason why aliens might be unlikely to come and take our water, because there's so much more easily accessible water without the solar system, not to mention all the other, probably more nearby solar systems. As I said, accelerating space probe, you can do that in various ways. So in our paper, we worked out how to do it using either coil guns. That was what we did in our calculations. And then sitting next to us was Eric Drexler, the father of nanotechnology, who started actually in his career by thinking about solar cells and how to make them better. And after a while, he got annoyed at us because the kids today obviously don't know how to make coil guns. Indeed, you can find some old pictures of him in Gerald ONeill's lab standing next to the railgun demonstration. So we started talking about using lasers. You can do some very cool things here by using some slightly weird shaped laser pulses. And then either solar cell or you have a perfect optical crystal, and you can get really big speed. But again, you want to send small seeds. So basically the idea is you build a Dyson Sphere, you send off the space probes, then they have a little rocket or something that slows them down. Then the seeds land on an asteroid and basically just build all of that again and then profit. Because basically what you can do, instead of just going for one galaxy at a time and jumping to the next one, intergalactic space seems to be very clean. There doesn't seem to be much dust. Because of various reasons, it gets eroded before it moves many thousands of light years outside galaxies. So what you do is you basically send probes to each galaxy, and then inside each galaxy, you settle it. So when you work out the math, you find that the main limitation to this is the expansion of the universe. So depending on how fast you go, that puts a limit on how far you can go. So if we travel at 99% of light speed, we can get 4.8 billion galaxies, each of them with about a few 100 billion stars. That ought to be enough for everybody. This is the entire visible universe. This is the stuff we could theoretically reach according to the laws of physics as we understand it. Of course, if we go more slowly, we get a smaller part. But that's how much we could reach. That's also true for aliens starting at the same time in some other spot. They can also get about this size. Aliens starting earlier, of course, get a much bigger bubble because the universe hadn't expanded as much when they were starting. So when you work out the math on various scenarios on rocket engines, etc., you can see how long does it take to get the solar power to launch all this. And it turns out that the longest of this is 6 hours. So that's where the 6-hour figure comes in conquering the universe in 6 hours. You first need to build your Dyson Sphere, and that's probably going to take you about 40 years of disassembling Mercury and putting it up. And then you build a lot of rockets, and then you launch them. And then you wait and wait and wait, because if you want to get a galaxy billions of light years away, actually you have to wait billions of years, so you better make a very sturdy rocket. Nearby the stars, on the other hand, you can get within a few million years and even less. And then in each galaxy, the little seed lands on an asteroid, unfolds solar collectors, gets some gravel, builds more solar collectors, more robots, and before you know it, you have a Dyson Sphere sending off probes to all the stars in the galaxy. And then you have it all. And this is essentially instant. So here's my little recipe, basically, for take over the universe. Yep. And you need one asteroid. I think actually Ceres is more than enough. You need your star. You need your self-replicating robot. You need a fair bit of patience. You, of course, need the technology to make something that can withstand this space travel at fairly high speed and function after a billion years. So there's some engineering that still needs to be worked out here. Some rather important engineering. But it doesn't look like it's against the laws of physics. So one question is, what's going on here? Because this is a very tiny amount of resources. Those galaxies, I mean, one star and asteroid in each of them, that seems very wimpy. And the reason is that I think we can describe intelligence as a kind of phase transformation of matter in the universe. You have matter moving around normally, then some of it turns into life, and then some of it turns into intelligent life, which start to reorganize matter using self-replicating robots and other forms of technology. And that's the change in organization. It's not so much that you move things around a lot. What this scenario is all about is we're sending off seeds to organize the matter in particular ways that make them better at organizing matter in other ways. So in a sense, we might be a very weird instability in physics, just like ice crystal formation or other things changing. Now, what does this tell us about alien intelligence? Well, it could be that the reason we haven't been spammed yet by aliens doing the same thing is that there is nobody around. The universe is ours. Or it could be that actually they have all weirdly converged on something. They all put us in a zoo, or they're all playing World of Warcraft, which is really weird, because that would suggest that there is something that gets all intelligent life to behave in the same way. As I said earlier, that's the strongest sociological claim I ever heard. It could also be that actually the universe is super dangerous. I have another paper making an argument that this might not quite be true, but it's still up there. The emptier the sky seems to be, the more dangerous it might be. And my argument means that we don't need to just concern ourselves with aliens from the Milky Way, but from all the other galaxies. Then, of course, another possibility might be they're actually getting started about now. This is not entirely unthinkable, because in the past the universe was a much more dramatic and dangerous place. There was much more star formation going on, including a lot of very big blue-white supergiant stars that tended to end their brief lives by blowing up as a supernova or a gamma ray burst. That tended to fry nearby planets, or at least land life would probably be in deep trouble. So you can imagine a kind of game of astronomical snakes and ladders, where essentially life was evolving towards more advanced forms, and then bang, it got smacked by a gamma ray burst. So it started evolving back up, and bang. But the rate of these gamma ray bursts have been declining exponentially over the past billion years or so. So maybe it's just that now intelligent life is finally emerging here and there, and we're all kind of started to think about the universe and what we could do with it. And that might mean that we need to scramble to our rockets. However, there's another thing also. In order to get the most of the universe, you need to go really fast. If we just rush away and try to build a rocket right now, it's going to be a crappy rocket. It might be that we actually need to rush to the physics lab and the engineering lab and come up with ways of moving faster. Because over long distances, faster rockets, especially on the cosmological distance, really, really outperform the slower ones. So actually, the race is going to go to the one that has a faster rocket. So that might mean that we should do way more research. And then we get to the universe. Thank you.